Welcome to the eLearnSecurity video lesson on how to use Wireshark to analyze protocols and capture files. Wireshark has a lot of features you can use to study packets during a live traffic capture or by loading a saved capture session. In this video, you will see how to use the tool to identify network routers and study the protocols running on every layer of the network stack. Let us switch to Wireshark and open a capture file. Capture files can be produced by Wireshark, other network sniffers, routers, firewalls, or other networking devices. Today, we want to open a file containing the traffic captured during the Using Wireshark video. To do that, we can click on the Open button of the main window and choose the file. Or select one of the recent files. So we click on Capture PTS to open it. As soon as the file opens, Wireshark loads all of the saved packets. A traffic capture can be overwhelming because of the huge number of packets and the amount of different protocols in use. But with the right approach, you will be able to study any PCAP file. Firstly, we want to show only ARP requests and replies by typing ARP in the filter input box, and then clicking Apply. Now Wireshark is displaying only ARP packets. As you can see, name resolution is enabled for MAC addresses. For example, we read broadcast instead of the byte value of the broadcast address. Moreover, the tool resolves network interface cards addresses to the name of the manufacturer, 3Com and Cadmus in this example. If we want to use raw MAC addresses, we have to click on the View menu, then move the mouse to Name Resolution and toggle Enable for MAC Layer. Now the packet list shows plain MAC addresses in the source and destination columns. Let us take a look at the first two packets. We have an ARP request asking for the address of 10.11.12.4. Then, there is a reply telling us to reach that address. That reply could come from a router. Let us call it our candidate router. To verify if 10.11.12.4 is a router or not, we have to clear the current display filter and check the content of the packets having the source and destination IP addresses in two different networks. These two addresses could sit in the same /8 network, so we choose another packet. These two packets do not share any prefix, so they must be on two different networks. If we take a look at the Ethernet frame of the packet, we see the MAC address of our candidate's router as the destination address. This confirms that our candidate router is actually a real router. While inspecting packet number 3, we can see that the link layer's destination MAC address is the address of our router. This helps tell us that 10.11.12.145 and 10.100.13.37 are on two different networks. Another way to confirm our hypothesis is filtering for packets having the router's MAC address as their destination MAC address. We can do that by selecting the ARP reply message containing the router's address. Right-clicking on the address, going to the Copy menu, and clicking on Value. This stores the router's MAC address in the computer's clipboard. We can use the address to build a display filter showing only packets sent to it. Let us type eth.dst space ==, followed by the address we just copied, and click Apply. As you can see, many packets with different IP addresses in different networks are displayed. This again confirms that the address belongs to a router. Carrying on our analysis, we find that packet number 3 is a DNS packet. To display only DNS packets, we type DNS in the filter input box and hit Enter. The Domain Name System Protocol is an application layer protocol used, among other things, to resolve Internet names to IP addresses. Wireshark can parse this and other protocols, letting us carry out protocol analysis in an easier way. For example, we can expand the DNS section of the current packet and take a look at its content. By expanding the query section, we can see that the host is asking for the IP address of the admin.site. We can tell that because the name field contains admin.site. The type field is an A, which means that this is a host address request. and the class field is Internet. After the request packet, we have a DNS reply. In the answer section, we can read the address 146.128.7.4. If we clear the filter for a moment, we can see the reason behind this name resolution request. The computer generating traffic was running an instance of the ping utility, so it needed to know the IP address to use as the echo request's target. We now reapply the filter and take a look at the DNS request packet, inspecting every protocol layer for information. DNS queries use UDP as a transport layer protocol. We can expand the User Datagram Protocol section to inspect it. As you can see, the destination port of the packet is port 53, a well-known port reserved to DNS. This is a request coming from a client, 10.11.12.145 in our example. And, as every DNS client request, it has port 53 as destination port. On the other hand, the source port is a random port, 34278. If we take a look at a DNS reply, we can see that the source port is the reserved one, while the destination port matches the source port of the client's request, 34278. Inspecting other packets, we can verify how every DNS query has a random source port and 53 as the destination port. While DNS responses have 53 as the source port and another port as destination. If you will recall, transport layer ports identify processes, both on the client and server machines. This is why servers use well-known ports. The following traffic contains ICMP packets. ICMP is a diagnostic protocol used over the Internet. As before, we filter the traffic by writing ICMP as display filter and hitting enter. As you can see, there are some ping requests and ping replies. If you look at the time column, you can notice that every request is sent a second after the other. This clearly tells us that the request was made by a ping utility application. Inspecting the packets, we see that this packet contains an echo request message, while this one contains no echo reply. Let us clear the display filter to show the entire capture session and continue our analysis. Scrolling down the packets list, we find some TCP packets. The very first 3 packets are used to perform the TCP three-way handshake. The first packet has the SYN flag enabled. We can verify that by expanding the transmission control process information and checking out the packet's flags. SYN is indeed set. The second packet has both the SYN and the ACK flags enabled. The third one has just the acknowledgement flag set. As you studied in the course material, during the three-way handshake, the hosts involved in the connection synchronize their sequence numbers. Please note that by default, Wireshark displays relative sequence numbers. Here we can see the first SYN packet. Its relative sequence number is 0. The SYN-ACK packet sent back by the server contains the server's sequence number. The number is also 0 because it is also a relative sequence number. Moreover, this packet carries the ACK number. Its value is 1 because ACK numbers are a simple increment of the sequence number received by the other party. Finally, to end the handshake, there is an ACK packet used by the client to acknowledge the sequence number sent by the server. In some situations, you might prefer to work with the actual sequence numbers. You can do that by opening the Edit menu, clicking on Preferences, then expanding the Protocols section of the Wireshark Preferences window. Going to TCP, unchecking the Relative Sequence Numbers checkbox and clicking Apply. As you can see, Wireshark now displays absolute values, both for sequence and acknowledgement numbers. We now re-enable the Relative Sequence Numbers checkbox in the Preferences window. Wireshark again displays relative numbers. Please look at the port numbers. Packets sent from the client to the server have the HTTP well-known port. The HTTP well-known port is the destination port, while the source port is a random one. As we expect, packets sent from the server to the client use the ports the other way around. After performing the TCP handshake, the hosts 10.11.12.145 and 146.128.7.4 are connected and can start the data transfer phase. In this case, the hosts are using HTTP. You will see how the Hypertext Transfer Protocol works in the Web Applications module. As we saw for DNS, Wireshark can parse application layer protocols fields and present them to us. Here we can see how the tool parses the request sent by the client to the server, identifying the method, URI, HTTP version, and headers. Analyzing the server's response, we can observe the same behavior. Wireshark parses the response and its headers. Here are other examples of requests and responses. Inspecting single packets does not give us a complete idea about the communication between two hosts. This is because of possible network congestion or because a capture file could contain traffic of many different parallel connections. In those situations, when packets arrive out of order, manually telling which packet belongs to which connection is simply very hard. To solve this, we can right-click to a packet belonging to the connection we want to analyze and click Follow TCP Stream. Wireshark then presents us with a window displaying all of the application layer content, where we can read client messages and servers. In this example, we are inspecting some HTTP traffic, a text-based protocol, but if you need to analyze some other traffic, you can rely on different visualization options. We can switch from raw to C arrays to hex dump, extended binary coded decimal interchange code, or ASCII. If we close the window, you can see that Wireshark automatically sets a display filter which shows only the TCP stream 0, the first TCP stream of the capture. To see the packets of the second connection, we can upload the filter and change the 0 to 1. As you can see, we have another three-way handshake and some data transmission. We can right-click to any packet of the stream and click on Follow TCP Stream to display the application layer messages in a single window. By using this method, we can easily switch between TCP streams just by updating the display filters. And this concludes this video on using Wireshark to analyze networking protocols and traffic capture files. We suggest that you try Wireshark as much as you can, record some traffic, analyze it, and study how protocols work. It does not matter if you will be a penetration tester, a systems administrator, or a developer. Being able to understand how computer networks and protocols work will be a great asset for your career. Thanks very much for joining us.